Let C be a positively oriented, simple closed curve containing the origin in its interior. Like, for example, maybe the unit circle. We would like to compute the contour integral along C of z cubed times the cosine of 1 over z dz. And to do this, we're going to use the residue theorem, which says that assuming that C is a positively oriented simple closed contour, exactly like we have stated here in the problem, and suppose that the function is analytic along the curve and inside the curve, except at finitely many isolated singularities, z1, z2, etc., up to zn, the list comes to an end, it's finitely many singularities. Then the integral of the function along the contour is equal to 2 pi I times the sum of the residues. So at each of these singularities, the function f has a Laurent series expansion. So let's say that Zj is one of the singularities, then there is a Laurent series expansion for the function centered at the singularity. So if the singularity is Zj, and we're using k for the index of the summation, so there is a Laurent series expansion about the singularity z sub j. Then the residue of f at zj is the coefficient c sub minus 1 when k is equal to negative 1. So the coefficient of z minus zj to the negative 1 power. So a term that looks like this should be in this series. And then this number, c sub negative 1, that coefficient, is called the residue of the function at that singularity. Now in our case, our function only has one singularity, and it's at the origin, because z cubed is entire, cosine of z is entire, but 1 over z has a singularity at the origin. So the composition here has that same singularity at the origin. So we only have one singularity. So our sum is just going to be one term. We have to find one residue. So we need to make the Laurent series for this function, and we need that center of that Laurent series to be 0. So in order to make the Laurent series, let's first just make the Maclaurin series for cosine z. Cosine z, and let's write it out in the long form. The summation form is not very convenient. We want to look for this term, so it's nice to see all the terms. Cosine z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, etc. And that means that cosine of 1 over z, replace all the z's here with 1 over z's. So if we put 1 over z here in place of z, that's going to move the z squared to the bottom and the z to the 4th to the bottom. So 1 minus 1 over 2 factorial times z squared plus 1 over 4 factorial times z to the 4th minus 1 over 6 factorial times z to the 6th, etc. And then just multiply through by z cubed. So z cubed times the cosine of 1 over z is equal to z cubed minus z over 2 factorial plus 1 over 4 factorial times z, because z cubed over z to the 4th will leave us with a z in the denominator, and this is the crucial term here, where we're going to get our residue, and then minus, if we multiply this one by z cubed, we have 1 over 6 factorial times z cubed, and this continues. So the residue of our function f of z, this one is f of z here, at 0, when we make the Laurent series centered at 0, the residue is the coefficient of 1 over z, and that coefficient is 1 over 4 factorial, which is 1 over 24. And so according to the residue theorem, this integral is equal to 2 pi I times the sum of the residues. So this integral is equal to 2 pi I times the sum of the residues. There's only one residue because there was only one singularity, and that is 1 over 24. So we can simplify, canceling the 2, pi I over 12.